Hello and welcome. Anybody who studies hypothesis testing would at some point or the other definitely come across this question that how do I choose the right hypothesis test? This video tries to resolve that specific query. So we will first divide the understanding of data into two broad categories. First is numerical data, essentially the data which is measured and is meaningful for arithmetic operations. And the other type of data, which is categorical, which essentially is non-numerical data where the arithmetic operations don't make sense. For example, we can talk about the choice of colors, we can talk about the genders, we can talk about the choice of different genres. Somebody likes an action movie, somebody likes a thriller, somebody likes a comedy. So these are all categories that we can divide them into, right? So the first section that we're going to focus at is involving the relationship between a numerical variable and a categorical variable. For example, you're trying to analyze the scores attained by different students from different educational backgrounds or different colleges. So the college or the educational background becomes a factor or a category, and the score that you're measuring becomes a number. Let's move to the right, and I'll create some space because I'll have to expand these notes further. When you're analyzing this kind of data, there are two possibilities. The numerical data is assumed to have come from a population which is normally distributed, or it has come from a population which is not normally distributed. This again can be checked through a test like a Shapiro-Wilk test or the Kolmogorov-Smirnov test. Let's say you found that the data is normally distributed. Now you're trying to analyze this further. So I'll expand this. How is the data presented to you? Is it one sample, one column which has the data, and you're comparing it against a hypothesized reference? If that is the case, then we have a couple of other possibilities. Is the population standard deviation known? Is that provided to you in the problem? And is the sample size, the number of observations in the sample, are greater than or equal to 30? If that is the case, then you can perform a one sample Z test. Notice what conditions are satisfied. Population standard deviation is known and the sample size is greater than or equal to 30. Then you perform a one sample Z test. When population standard deviation is not known, but the sample size is greater than or equal to 30, you can still perform a one sample Z test. I know there is some literature that talks about using a t-test, and a lot of people use it when the population standard deviation is not known, but still I would vote in favor of a one sample Z test in this case, because the sample size is greater than or equal to 30. Now, if the population standard deviation is not known and the sample size is less than 30, then you perform a one sample t-test, right? So this was one sample and you're comparing it with a hypothesized value or a reference. What about comparing two samples and when they are independent? What do we mean by independent? These columns, these two columns containing the numerical data, are not relative to each other. They don't have any overlap. If that is the case, we can check if the variance is equal. We can do a Levene's test for that. If the variance is equal, we can perform a two sample t-test. If you want to get deeper into each of these tests, then I'm providing a comprehensive playlist which explains every single test with solved examples. So we've explained these tests to you right from scratch with manual calculations, as well as using a tool where you can solve it in seconds. Both the approaches have been explained to you in the comprehensive playlist that I'm attaching to the description of this video. You may refer to it. Proceeding, when we have two independent samples, but the variances are not equal, then we perform a Welch's t-test. In libraries like SciPy and Python, this is adjusted by just giving a different parameter input. Very easy. Now, if these two samples happen to be dependent, which means they are like before and after comparisons, and the observational units are one and the same, you have a before value and the after value, then you can perform a paired t-test. Let's say you have more than two independent samples, then once again, you can check for equality of variances. If the variances are equal, you can perform analysis of variance or ANOVA. But if the variances are not equal, you can perform something that's known as the Welch's ANOVA. So this takes care of all the tests which assume the data is normally distributed. Such tests in general are also referred to as parametric tests. These tests that we've talked about are the tests of mean. Of course, a mean is meaningful when the data is normally distributed. But when the data is not normally distributed, it may not make sense to compare the means any further. And mostly these will be the tests of medians. Let's move to that. When you compare one sample against a reference, you can perform a one sample sign test. When you're comparing two independent samples, no relationship between the samples, no overlap between them, you can perform a Mann-Whitney U test. When you're performing a test on two dependent samples, which means it's like a before and after comparison, it's just that you're not comparing the means any further. You can perform a Wilcoxon signed rank test. And when we are comparing more than two independent samples, we can perform a Kruskal-Wallis test. So if I put it together like this, one sample sign test is equivalent of these one sample Z or T tests. Mann-Whitney test is an equivalent of the two sample T test with independent samples. And a Wilcoxon signed rank test is equivalent of a paired T test when the dependent samples are there. And a Kruskal-Wallis test is equivalent of the ANOVA. Now let's move to the left of this chart and see this a little better. So when we have one numerical variable and we are analyzing it with respect to another numerical variable. So two columns, data is numerical continuous data. Best check here would be something like a correlation or regression. Correlation, you know, is a value between -1 to 1, both inclusive, and it tells us whether the variables are moving in the same direction or opposite direction. So that's the best analysis that you can perform when you have two numerical variables. When you have two categorical variables, one categorical variable with respect to another categorical variable. So for example, let's say one variable is the qualification level, which could be a graduate, postgraduate, or a PhD. And the other variable is the interview result, whether the person got selected or not, right? So these are two kind of categorical variables. One is selection, the other is education. And when you're trying to analyze if they have any association, you can analyze it in two ways. You can either perform a test of proportions. Again, the data should be like that, and we've explained this in the videos further. The playlist is attached in the description. Or we have the data in a tabular format. We can bring it to a tabular format, and then we can perform a chi-square contingency test. So this, in a nutshell, puts together all the hypothesis tests. So we are not claiming that this is an exhaustive list. Of course, there are more tests that are available. But the point is that if you know this much, I think you'll be sorted 99% of the times. You don't need to know anything else beyond this. And like I mentioned, you know, this content is already available in the playlist. We are providing you as a part of the description of this video. So go through the videos and keep clearing your doubts related to each and every test. Everything is solved in these videos right from scratch using relevant data examples. And we've also demonstrated the use of tools. Hope this video answers most of your doubts related to hypothesis testing, especially related to the choice of tests. Thank you.